think people can see my screen? Can you see the screen? If somebody can see, let me know.
Yes, I can see.
That's great. Yes, this is, I'm just sharing the timetable, what we'll be doing in the next days. So, as we know, we want to quickly look at, the workshop is on comparison of more than 2 means. When you have 3 or 4 or 5 means, you're comparing them. That's what we are looking at. And that is, we use Anova. If we assume that the data set follow normal distribution, we use Anova, and so we're going to be talking about Anova. If it doesn't follow normal distribution, the non-parametric counterpart also, we are going to consider them. The Kuka-Wallis test, the Friedman-Anova, and median test. These are the non-parametric counterparts. So in the next 3 days, today, tomorrow, and next tomorrow, we want to understand the concept of family-wise error. That is the reason for not using t-test to compare more than 2 means. And the theory of Anova, the logic behind it, and the logic of the F ratio, that is the statistic of Anova. Then the F distribution, just like the way we look at chi-square distribution, t distribution, and normal distribution, we want to look at F distribution. So by tomorrow also, we look at, in some situation, when you find out a difference with Anova, you either do a Planck contrast or post-hoc test. Tomorrow we'll be looking at that. We cannot look at Planck today, but tomorrow we'll look at Planck contrast and post-hoc test. And also the factorial Anova. When we have more than one factor, we call it factorial Anova because the simplest one is the one-way Anova. So when we have more than one factor, we look at factorial Anova. All those things, we're going to do them practically. We're going to look at their theoretical basis and use data. We're going to run it with data. Use SPSS to run it to see the way it is. The repeated measure Anova, then non-parametric counterpart, Kuka-Wallis, Friedman, and median. Those are the things we want to be looking at the next 3 days. So I think we can start now. So if Dr. Wanye want to receive, have they received? Dr.
Yes, I've seen the mail. I'm just trying to download the file.
Okay, what of Professor Tokidem? Have you received?
Yes, sir, I have.
Okay. So, Wanye, hello?
Sir.
So if you send your email to Ugo so that they can forward it to you also. Can you?
Okay, sir.
That's okay. Send your email to Ugo. Please go ahead and forward it to her also. Now, before I start, I want to know our expectation in 2 minutes, 1 minute. What our expectation, because nobody can, you pay money, your time, because everybody is busy. All of us you are all professionals. You are one thing or the other. It must be a serious business. Number 1, to devote your time. Number 2, to pay your money. Even the person that just saw it and joined, if the person doesn't value it, he will not join. No, that's just it. So those are the issues. I want expectation. What are your expectations? I just want to be in 1 minute before we start. What are your expectations? Because it's good to know that, so that I know. Because I like customizing what I'm doing to the taste of the client, the people. So I like customizing. So 1 or 2 persons can talk. What are your expectations in this workshop? Or there's no expectation. If there's no, so we can just continue. But I'm sure we have expectation. Oh, sorry, Dr. Lagujo, you were calling me. Sorry. Yeah, oh, no expectation? So, Dr. Ebenezer, no expectation? What are your expectations? Even if it is 1.
To independently run Anova and the parametric test, non-parametric test.
Non-parametric counterpart. Okay.
Can you hear me? Can
Yeah,
you
I can hear you.
can you hear
I'm
me?
hearing you, sir. I'm hearing you.
My expectation is that at the end of today or at the end of the entire workshop, I should be able to independently run
Yes, on
all
your own.
aspects of Anova and the non-parametric counterparts on my own.
That's great. So that is great. That's a very good one. Yes, it's what we that is what we are targeting, and we did it last week. And it was powerful. I believe this one will be more powerful because I got to try to get people's feel about it so that I can customize it. So we'll drive it. Any other one, Prof? You want me to be calling him?
Yeah.
Yeah. Okay, no expectation, Prof. Rush back.
So, well, to be able to master the skills in doing the factorial ANOVA.
Oh, factorial. I know that is the highfalutin one, the Prof one, the advanced one. It's okay. Yes, it's okay. Rush back. Okay. Okay, no other person. I know that Ugo, you are around. You have expectation, and Dr. Olagboye.
My expectation is to just to reinforce what I've already learned in terms of ANOVA and practicing it, like running analysis for ANOVA.
Okay.
Thank you, sir. Please, so you've not sent the email for the last person.
No, let her, if she wants, Abalaba, when you chat your email to Ugo,
okay.
You see Ugo Naya there. Okay, I think we'll start right away. Yes, we are, I know that by the end of this training workshop, you should be able to conceptualize. So, and you know, there are three things that serve as my hallmark in my statistical lecture and training. Number one is for you to learn statistics without being bogged down with equation or formula. Because, you know, some people, when they want to, they say random variable is the variable how divided by, you know, even in trying to explain, they mathematicalize everything and they confuse people more. So because the mathematics, the graph, equation, all those things, they are modeling real life situation. If you allow people to conceptualize it the way it is real life, it is easy. No, it is easy. So I try to help you conceptualize statistics without being bogged down in the equation. Then to move, the second one, to move it from the fundamental, the most very basic, to advanced level. So gradually, you will know when you understand the advanced one. By the time you start from, it's just like you are climbing, even if it is 50 story or 100 story. You know, if there are staircase there, it's just a matter of gradually, step by step, you get there. So the third one is for you to to give you an approach, a simplified approach to be able to use machine, a software to run your analysis because nobody calculates with hand again. That was when there was no computer. Now we have computer software there. Why do you bother yourself? It's just for you to know the logic. When you know the logic, then know how to use machine to do it. So some people are now say, okay, why not? Better look at the people were trekking before now. Move from Lagos to Abuja, people were trekking. They spend days on the road. But now you take flight. There is no car. Flight 1 hour, you are there in Abuja. So now we all understand that when we compare means, that is when we have an output variable which is quantitative. So we summarize our output variable. When you say quantitative, numerical, by calculating mean, standard deviation, and median, mode, all those range. All those are the things we use to, the statistics we use to summarize our quantitative variable. So when you are having group, we are comparing group A, group B. You have summarized them, their mean, you want to compare. This mean look bigger. One is 65, one is 60. This difference, this statistically significant. Of course, when it is only two groups, we can easily do two t-tests. Then when we have more than two groups, we cannot do. So there's an assumption that the people here will understand the t-test, because you cannot go back nitty-gritty and be explaining the t-test. But of course, we are going to explain why we cannot use t-test to compare more than two groups. The training we did before this one was on all the t-test concerning two things. Now, though we are repeating the training because of that. So of course, we talk about three types of t-tests then: pair t-test, one sample t-test, independent t-test. Now, when you are comparing more than two means, analysis of variance is what is being used. Analysis of variance is a statistical method employed to compare means of three or more groups, and 4 groups, 5 groups, 3 groups. It is good to know that you cannot use t-test because of what we call family-wise error. So I will not go back. So somebody is that's from Wayne's place. So now the logic behind all this is that when you state your null hypothesis, you know from the outset of your study, when you are deception, you have to determine, when you are stating your hypothesis, you have to determine at what level will you reject type 1 error. That is your level of significance. So at what level will you use okay? You reject null hypothesis rather. That is, at what type 1 error level will you accommodate? So conventionally, arbitrarily, people choose 5%, but you can be more stringent by choosing 1%, but nobody chooses more than 5%. That is, the logic behind that 5% is that because what you are testing is the difference I'm seeing when I do my descriptive statistic. Maybe you have 3 groups. You can see the mean of one, maybe is hemoglobin concentration. Mean of one is 15%. In 15 milligram gram per day. The mean of the other second one is 17. Another one is 18.9. You see these 3 groups. You can see difference: 15, 17, 18.9. There are differences. You can see difference, but this difference is due to chance, and that is what. So what you are trying to do when you state your null hypothesis, you want to be sure that you will not conclude that there's a difference in real life when there's no difference. So that mistake is what is called type 1 error. Rejecting one null hypothesis when it is true. That is, when there is no difference, say there is a difference. That is a mistake. So, but you cannot be 100% sure, and that is why people sometimes, if the probability is 1 that you are making a mistake, it is certain you are making a mistake. If it is 0, it's sure that you are not making. But in recent, it's in between 0 and 1. So in that case, you have to choose an activity. People choose 5%. That is, that 5 is that's p-value. The level of significance is the level you want to reject null hypothesis, because the probability, the p-value, is the probability that you have. You say there's a difference when there's no difference. So if the probability can be as low as 5%, I want to say it's minimal. Anything less than that, let's just say that's a difference. So that is the level of significance usually set. Sometimes you can set 1%, which is 0.051. But 5% is 1 out of 20. That is your type 1 error rate. You can accommodate. But what is happening here, whenever you are doing many tests, it is believed that there's a chance when you do many tests, that a chance that at least 1 or 2 will be will be significant, even in the real, even though in the real life it's not supposed to be significant. We may find out that one is significant. It's just like if somebody doesn't know anything, go for exam. Yeah, especially this objective. If you continue writing one day, if he pass, doesn't mean that he knows something. If you continue making attempt, continuously, one way or the other, it just get through. So it's just like the logic in medical school. They say that because they usually have multiple questions, yes or no, about 500, even sometimes more than 500 in one exam, one course, you are good to write. So if they say that even someone that has not gone to medical school, if you give the person, when you are answering a question that is close to 1,000, and it's true or false. So even if you are just gambling, because when you gamble many a time, you are going to get 50-50. You're like if you toss a coin 1,000 times, it's going to be 50-50. Head or tail, head will be 50%. And the pass mark is 50%. Even in some courses that their own pass mark is 40%. So even someone that doesn't know anything, if you gamble because the question is plenty, he will, before you know, he will even score 50. So that is why they try to remove negative mark. So what I'm just saying is that whenever there are many attempts at a particular thing, there's a possibility of you getting result. That is what is happening here. So there are two things I want you to look at. Want to see how do you arrive at the number of tests you carry out. That is, if you are to carry out T tests, we are trying to give room, family-wise error. The reason we don't use T tests, that's what we are establishing now. If you are to carry out 3 for 3 group, how many T tests can you carry out? For 4 group, how many T tests? For 5 group, how many T tests? That's number one. Then how to now calculate the family error, the error rate for each of them. So if you look at this, if you remember combination, formula for combination, it's very simple. Even though I say that I don't bore people down with equation or formula, but I will explain it to you so that you don't even need to cram it. So when they say combination, this formula you are saying like n combination, how that is, how many times can you combine n number of items in Haru way? Our example now, if we are to apply it to T-test, because T-test is about two means. When you say you are carrying out T-test, you are carrying out 2 means, you are comparing 2 means. So if you have 3, if you have 2 means, 1 and 2, it's only one way you compare them. But if you have 3, A, B, C, group A, group B, group C, and every way is pairing, that is 2, 2, 2. You want to group them 2, 2. How many ways can you group 3 things 2, 2, 2? That is the meaning of n combination. Haru is the 2. N is 3. Let's say it's 3 now. You know you have A, if there are 3, 1, 2, 3 group. 1 and 2, that is one way. 1 and 3, that is second way. 2 and 3, that is 3 way. So there are 3 ways you can pair 3 items or 3 groups. That is, you can arrange them 2, 2. There are 3 ways. If there are 4, there are 6 ways. Look at it here. So is the formula combination we apply here to know the number for the group of mean you have for the number of T-tests. If you are to carry out T-tests, the number of T-tests you carry out. For example now, K actually means the number of group, which is synonymous with the N. Then we have already said because it's T-tests we are talking about pairing. So our R is 2 constant, 2 here. So K factorial over K minus 2 factorial. Factorial 2 factorial. If you do it for 2, of course it will be 1. It's only one way you can pair 2 things now. If there are 3 groups, you can pair them 3, as I've explained. If there are 4, you can pair them 6 ways. For example, if you have A, B, C, D, A and B, that is 1. A and C, that is 2. A and D, that is 3. B and C, that is 4. B and D, that is 5, C and D, that is 6. So if there are 4 groups, you can pair them 6 ways. If there are 5 groups, you can pair them 10 ways. Can you imagine? If there are 6 groups, you can pair them 15 ways. Then if there are 8, 20, if there are 7 groups, that's 21. Wait, 8, 28, 9, 36, and 10, 45. So now, those are the number of T. If you have to carry out, if we have 3 groups, you have to carry out T tests. We will carry out 3 T tests. For 4 groups, 6 T tests. For 5 groups, 10 T tests, and so on. That shows that the number of the T tests you carry out for that particular data set, just to find out difference among the 3 or 4 or 5 groups, increases as the number of groups increases astronomically. And the possibility of you getting some to be significant, when in actual sense is not to be significant, is very high. So we have seen the way we know the number of ways we can pair groups now. Then let's now look for how do we calculate the family-wise error. It's very simple. The family-wise error is the last 2 columns here. The family-wise error rate will be 1 minus 0.95 raised to power the number of tests you are carrying out. How does it happen like that? For example, you know, if you choose 5%, your level of significance will be 5%. That is your level, that is the probability of you committing type 1 error. The probability of you not committing type 1 error will be 95. That is your level of confidence, 95%. That is 0.95. If your significance level is 0.05, your confidence level of the level that you have not committed type 1 error is 0.95. So if you carry out 3 tests now, you now say is 0.95 raised to power 3. 0.95 times 0.95 times 0.95. If you now get it, you give it 0.8 something. When you now remove it, 8.4 something. If you now remove it from 1, it will now give you 0.143, which is 40%. Can you see? Whereas you start with your level, your significant level was set as 5%, which is 0.05. But by carrying out 3 tests, it has jacked up to 40.3%. Can you see? If it is 4 groups you are dealing with, so you are carrying out 6 tests, it will jack up to 26.5%. Can you see? If you apply this formula to it. If it is 5 groups, you are carrying out 10 tests, it will jack up to 40%, 40.1%. If it is 15 tests you carry out, it is 53. Can you imagine? If it is eventually 45 tests you carry out, maybe there are 10 groups. In fact, your error is 90.1%. That is what we call family-wide error. That is, family-wide just means that when you are family in a group, so when you are carrying out a group of tests on a data set, a group of similar tests, like you are doing T tests for the same 10 T tests, 6 T tests. So there's a possibility that some will be significant, while in actual sense there is no even significant thing here. That is the family-wise error rate. And it increases with the number of groups. So I don't know. Before I move further, I want clarification on this one, this family-wise error rate. Any clarification? It's because of this error rate that people now, so you don't carry out multiple T tests whenever you're having more than 2 groups. You rather opt for another test. That was why the intelligent people now develop Anova. So I don't know. I
have a question, sir.
Yes, sir. Yes, sir.
Can we have more than 10 groups?
You can have more than 10 well, if you're a researcher. If it's possible that somebody have 10 groups is comparing to me, why not? They say there's never a mercy. Even though it looks hypothetical, it can happen.
In that instance, the family-wise error rate will be more than.
It can even be 100%.
Okay.
It's approaching on. If you look at it, it's approaching 100% as the number increases. It's approaching.
Dr.
Balogun.
Yeah, this is just out of curiosity.
Okay, sir.
If using t-test alone, we are finding so many reasons to incriminate the test when it involves more than 2 groups. Does it mean Anova doesn't have its own error rate? Because if you are saying because t-test, you are not good, you are not suitable.
If you look at it, what brought the error? You know, what they are saying is that the error is applied to one test. If you say 0.05%, yes, which is a 0.05, which is 5% as your level of significance, is applied to one test. But what we are saying that if you are carrying out 2 or 3 of the similar tests at the same time, so it increases it. So what Anova does is just to carry only one test. Either you are 2 group or 3 group, you carry out one test. I don't know why somebody is calling me when I'm doing lecture. Is it supposed to be here? Hello, I'm in a lecture. I'm in a lecture. Okay. Let's see if you want to join. So, I don't know if you understand, Dr. Balogun. Is it clear?
Yeah.
Yes.
Since
so Anova just one test.
Anova is just one test.
Yes.
Then we also say the error rate in Anova is 0.05. Abi?
Yes. You use 0.05. You use 0.0 because that's what you said for your research.
It remains now.
It remains 0.05 since it's only one test, one Anova you carry out. But if it's significant, we are going to say later that you have to find out where does it, because the Anova will not tell you where the different lies. We'll talk about that later. Any other question concerning the one we have done? Any question? Any clarification? So we should go on. Okay. Let me just continue. Great. Now, yes. So the Anova, the statistic is F. So we also call it F test. But that's not the only F test. That's another thing. So what it does, whether it's try to test these 3 means or 4 means or 5 means, are they the same or not? Just like what the way other tests, t-test test. T-test test if 2 means are the same or not. So but this one is 3 or 4, this means are they the same? The F statistic is the same logic as T statistic, because if you remember, I said that all statistical tests, they are the same cloth. The same thing, put in a different cloth. So you see that it has to do with division. There is numerator, there is denominator. And what does numerator does? Numerators try to look at what is the difference I'm seeing, the difference I'm seeing in my study. You can call it systematic difference, systematic variation. Someone that did tests, even this one is irrespective of whether it's 2 group or 3 group or 4 group, whether it's t-test or Anova. This test statistic is looking at the systematic variation divided by unsystematic variation. What do I mean by systematic variation? When you say you have 3 mean or 2 mean, you can see in your descriptive statistics they are different. That different, it may be due with what you observe in your experimental research or your observational research, it doesn't matter. But that is what you have seen in your study. That is a systematic variation. This variability you are seeing, the difference you are seeing among the group is systematic in the sense that that is what your study is looking at. But there is some other variation that your study cannot account for. Some of them may be inherent variation, or even your study did not account for the variable involved in it. That is the unsystematic variation. So what you're actually doing is to divide the systematic variation, which is the numerator, by the unsystematic variation, which is the denominator. If you remember, if I go back, I thank God I put it there. If you remember in our t-test, I talk about dividing the difference between the two means by standard error. Standard error represents the inherent variability of variation in the population. So it is when you look at the t-test, you look at the difference between the observed and the expected over the standard error. Is looking at systematic variation as the numerator over unsystematic variation. You can only say the difference is significant when the systematic variation, which is the numerator, is far, far bigger than unsystematic variation. Not just bigger, it has to be greater than 1. Not only greater than 1, it has to reach a critical level. And that is why you usually put the systematic variation at the numerator, so that if it's going to be significant, it should be bigger than 1. Not only bigger than 1, reach a critical level. And I say, no, you will not say, oh, this difference we are seeing is not due to chance. And that is why for most of the statistics, as the statistic increases, your probability of making that happen error decreases. That is why as your statistic increases in size, your p-value decreases. It's only Wilkinson and Mann-Whitney U that move in different directions, in the same direction. As the statistic decreases, the p-value decreases. That's the only Wilkinson and Mann-Whitney. For that is the non-parametric counterpart of t-test, student t-test. Those are the non-parametric counterpart of t-test. They are the only statistic that, as the value decreases, is not significant. Every other statistic is the opposite. As the value increases with many statistics, the significant increase. That is, your p-value will decrease. So the Anova is not an exception. It's like that. We are dividing something by, so what we are dividing as the numerator, is the cross of our discussion. And once you understand that, Anova is very simple. It's just logic. It's just logic. Once you understand the logic, it's very simple. So the statistic is called F ratio. That is, when we say ratio, it signifies that you are dividing. To remember your physics, ratio is when you divide one quantity with another quantity of the same unit. I usually give you an example. If you say you divide 400 kilometers over 4 hours, that is 100 kilometers per hour. That is not ratio because it has unit. The kilometer over hour. The numerator differ from the denominator. In the unit, they are not the same kind of thing. But when you divide 400 kilometers by 4 kilometers, it gives you 100. It's not 100 kilometers, it's 100 because the kilometer as the numerator has cancelled out the kilometer as the denominator. It becomes a ratio. So when you divide two things of the same kind, it gives you a ratio. So in this case now, when they call it F ratio, we are dividing something of the same kind. Something, though they are two different things, but they are the same kind. So that I give us a dimensionless value, which is a ratio. It is called F test to reflect the name of the person. Fisher, Ronald Fisher, Sir Ronald Fisher. So he's probably the cleverest person ever. Look at the p-value there. Those are the father of statistics that developed statistics in those days. He was a genetics. So he was the one that all this study design, they started, having, they will plant some crop on one plot, another one. So they are the one that started. He was the one that wrote statistical table. So Fisher, even Fisher is that you can hear many things about him. So Now, let's quickly look at the theory of Anova. Now, as I said before, this Anova examines variation across all the groups at once using the concept of variation between groups divided by variation within groups. You know what I mean by variation across all the groups? If you are comparing 3 groups, you already said that it's for more than 2 groups. If you are comparing those groups, even though the same logic applies for 2 groups, it's only that we already have used it to compare 2 groups. It's the same logic. So when you are, there's a variation between groups and there's a variation within groups. So what he compared is to compare the variation between as the numerator divided by the variation within as the denominator. The variation between is the systematic variation. The one within is the unsystematic. If there are no differences between the group, then the ratio of the variance between the group and within the group should be 1, since the variation will be the same. That is, if you say your variation between the group, if it maybe let's say it's 9, and variation within the group is 9. When you divide them, it gives you 1. If numerator and denominator are the same, it gives you 1. That's why there's no difference in within and between. So you cannot even talk about significance here. There's no even difference. If the variation, what you are looking at as you observe different, is even equal to the inherent variability, the one you cannot even account for, then you cannot say there's a difference. So if the group means are different, then the variation between divided by the variation within will be greater than 1. If the group mean you are looking at, you are comparing the 3 means or 4 means, if they are actually different, when you divide that variation between them by the one within, it should be greater than 1 and reach a critical level. You now say, oh, this difference is not just by chance. Anova is an omnibus test. That is, you know, I was telling Dr. Balogun the other time, is an omnibus. What it does, it tests overall effect. Okay, these 3 groups, is there any different anywhere? That's what it's testing. If there's a different anywhere, it will not tell you where the difference is. But if there's no different anywhere, you can rest your case. You can just believe that there's no even point to say where there's a different line. If it tells you and say there's no different anywhere, because there's no different anywhere. But if there is, it cannot tell you where the different line. For example, now assuming 3 means are being compared, every ratio may tell us that the means are not equal. You know, if you are trying to say mean 1 by x is mean for mean 1 is equal to mean 2 is equal to mean 3, is not true. That's what no hypothesis say those 3 means they are true. Then alternative hypothesis say they are not true. And that's what you are trying to test. If there are several ways, if actually there's no difference anywhere, yes. But if there is, there are different ways. It's not just only one way that can be different. Look at the first one. Mean 1 is not equal to mean 2, is not equal to mean 3. There's no difference anywhere. That's what it means. That's one scenario. Look at, there's a difference, rather, there is difference across. That's what it means. This one that says is equal to is the one that is no different. But this one that says this one is not equal to, is not equal, that shows that there are different everywhere. Now, the mean of, that's one scenario. Another scenario, the mean of 1 and 2 are the same, but group 3 has significant different mean. And you see, mean 1 and mean 2 the same, but they are not the same with mean 3. So it's mean 3 that differ from the other 2. That's one scenario. The another scenario, the mean of the group 2 and 3 are the same, but group 1 has significant different mean. That shows that you are now looking at 2 and 3 are the same, 1 differ. Then you can have mean 1 and 3 are the same, but group 2 are significantly different. And you see, it's only 1 and 3 are the same, 2 differ. So if you say there's a difference, these are the 4 different ways that can be different for 3 groups. So if there are 4 groups, you can be sure that maybe it will be up to 10 ways that can be different. Now, for you to conceptualize it very well, it is better we use an example. And the example we use is so straightforward that I beg you, it is if with this example, once you understand the logic of that F ratio, the variance between and within, I'm going to illustrate with this example, everything is done. That is the logic of Anova. Now, for example, let's say we have 3 groups that we have score, the libido score for these 3 groups. And what defines the 3 groups? As group 1, this group 1, you can call it group 1, 2, 3. But group 1 was given placebo because these studies try to look at the effect of Viagra on libido. So they gave a group placebo, they gave another group low dose Viagra, the third group high dose Viagra. Don't connect to the smile. So, yeah. So you lock the door, go open. So you group 1 placebo, low dose, group 2 high dose, group 3. Now you see after that they now score their libido, maybe on the scale of 1 to 10 or whatever. So when you can now see the value for each of them. Group 1 is 5 of them, group 2 5 of them, group 3 5 of them, making total 15. Yeah, 5, 5, 5. And the mean, look at their mean. If you add all these, each of the 5 together now, and divide by 5, you get the mean. Group 1, 2.2, group 2, 3.2, group 3, 5. Look at their standard deviation and look at their variance. Now, you have already known from it that you can see the group mean, each of the group mean. Then there is a grand mean. That is, if you collapse all the 50 together and divide by 15, you get the total mean, grand mean. And you can calculate the standard deviation and the variance. So the grand mean and the grand variance. Now, another way you can calculate the grand mean is to add the 3 means together and divide by 3. It will still give you the same value. But the one that is easy to conceptualize, which is most useful, is add all of them together, irrespective of the group they belong, and divide by the total number to give you the grand mean, and you can calculate the variance. I don't know if I should go back because I did something last week, because I don't want to assume that people understand calculating variance. Go and give out the something. I don't want to assume that people understand calculating variance. So I share one of the slides I use for descriptive statistics, how I explain variance, and I want to do that so that we can understand. I want to be sure that you understand the logic, because variance, many people look variance. When they say what is variance, many people will confuse mean square deviation from the mean. People get confused. Why people get confused? Because they have not understood the logic behind it. Let me share that one. I want to share that that particular slide. Just 1 minute. Let me share the slide on calculating variance. Though we calculate it better, I'm looking for a fundamental, a simpler way. The one I use when I was doing descriptive statistics, explaining descriptive statistics. I want to use that one to explain the way we calculate variance. Descriptive statistics, yeah, is it? Yes. You know, in descriptive statistics, when you are summarizing quantitative variable, you use mean, standard deviation, you use mean, mode, median, then standard deviation, range. Now, the mean, mode, median, they are measure of central tendency, in the sense that they are the value that represent the whole, as representing the whole, either mean or mode or median. And you know that if something is normally distributed, mean, mode, and median will be the same. We are not talking of that now. They just know that mean, mode, and median. And out of them, mean is the one that is most useful for advanced statistics. You know the reason? Because it is gotten by, you add all the value together and divide by the number. So all the value contribute to the mean. The mode is just one value that appears most, the one that is most frequent. Median is the one in the middle. At most, if it is the number of your entity is odd number, it's only one number in the middle. If it's even number, as per maybe there are 400, is the one 2 in the middle, and you can calculate the average of the two. So it's the mean that is more universal. Is though there are advantages at the rate of each of them. So the mean standing for the measure of central tendency. Then when we now talk about central tendency, that one alone cannot describe data set. For example, if you say in Dr. Olagunjoye's clinic, the average systolic blood pressure of the patient is 110. Now, in another person's of maybe Dr. Larry's clinic, Balogun's clinic, he says 110. Does it mean that the distribution of the patient is similar in both clinics? It may not mean. Because in Dr. Balogun's clinic, the mean may be 110, but people may have value that are very close, maybe 107, 105, 115, is around that 110. But in Dr. Alago's clinic, even though the mean may be 110, but the values may be far apart. We may have somebody that has systolic blood pressure of 90, even less than that, and somebody has 150, 180. So in that case now, both of them have the same mean, measure of central tendency, but they have different dispersion, how far apart each value is from the center. In Dr. Alago's clinic is wide apart, while in Dr. Balogun is very close. So that is why intelligent people now came with measure of dispersion. Apart from you knowing the mean, you want to know how apart they are. And one of them is variance. Variance, standard deviation, and even range, interquartile range, many things. But why I'm repeating this, the most important of them is this variance and standard deviation. It's actually the variance. It's only that the variance, the reason people don't quote variance, because it has a square element. But let's look at it. How do we, these are a data set, simple one, that show how you get variance from the data set, from the mean, after you have calculated the mean. Let's examine the subject. Let's just assume that this subject are 5 families who are family friends. There are 5 of them. Maybe they went for picnic And this X, this family 1, 2, 3, 4, 5. This X is the number of children in this family. You have 3 here, 4 here, 5 here, 6 here, 7 here. When you add the number of children, which is X together, it gives you 25. If you want to calculate the average number of children, the mean will be sigma. Sigma X means addition of X, which is 25. So the mean by X will be sigma X over N, because the sample size is N. There are 5 families here. So it gives you the average is 5. That is the measure of centeredness. Now, if you want to learn, want to know how wide apart are they, how far apart, averagely, are these individual value from the mean? Because sometimes the mean may not exist in the data set. That is, you might get a value that there's no even one. This one, it happened that one person, one family has 5 children, which is the mean. Then sometimes you may even get the mean average. You may be even decimal. For something that doesn't not even have decimal, you can even look at number of children, you can get 5.1. And you cannot actually have 5.1. So sometimes the mean may not, that's one of the disadvantages. Very easy. It's still the most useful measure of center tendency. Now, you want to now know that mean value, how far apart each value from the mean. And the way to do it is to look for what we call deviation from the mean. And this is deviation from the mean. X minus X bar. X bar minus X minus X bar. X bar is the mean. So because mean is in the middle, it's in center, as many value will be less than the mean as they are more than the mean. So if you try to remove mean from each value, those values that are less than the mean, when you remove mean from them, they will give you negative value. That's what you are seeing here. Those values that are more that equal to the mean, when you remove mean, it gives you zero. Those values that are more than the mean, when you remove mean, it gives you positive. If you make any attempt to add deviation from the mean, all of them together, it will give you 0. Because mean is in the middle, you're going to have as much negative value as you have the positive value. When you're adding them together, negative will cancel positive, give you 0. So it's like there's no way again to go. The intelligent people now can know it cannot happen. They now square. Can you see? They discover that there's no much they can do with deviation from the mean. They square the deviation from the mean, knowing that if you square it, it will give you negative, that's negative will give you positive. So it eliminates the positive value, the negative value rather. So when you square now, this square is what called square deviation. This is deviation, square deviation. Why did you say deviation? It's actually deviation from the mean. When you see square deviation from the mean, the mean. So when you add all the square deviation together, that's called sum of square deviation. They use it, sum of square. You're going to see, that's what you're going to see in Anova and regression. You will see sum of square. It's actually sum of square deviation from the mean. It's only that they shorten it, sum of square, sum of squares. These are square deviation, because deviation from the mean without squaring it is useless, because adding together it gives you 0. So you always square the deviation. When you add it together, it's sum. Of course, the problem with sum of it's just like the way you add the total value together. It didn't do you anything. You are looking for average something. You now divide the total by the number to give you the mean. It's the same thing here. You want to calculate the average sum of square. After you have average square deviation rather. Average square deviation. So you do that by dividing the sum of square by, you will not divide by n, you divide by the degree of freedom. Because the reason is very simple. The degree of freedom is used instead of n. Here, when we're calculating mean, we divided by n. But here, when we want to calculate the variance, we divide the sum of square deviation by n minus 1, the degree of freedom. So why? Because here, when you were dividing, you were calculating mean. You have not calculated mean. But here, when you want to calculate variance, you have already calculated the mean and already fixed everything together. You're like, if you know the mean now, you don't need to, if you know the mean, you just know, okay, how many children? You say 5, and the mean is 5. That shows that the total number of children will be 25. Average, you say average number of 25 for a family is 5. And the number of the family, they are 5. That shows that the total number is 5 times. So the mean, once you are calculated, it has fixed the rest, the total. So not every entity here can vary. And the logic behind it, when you have already fixed, when total is already fixed, you cannot, not all of them can vary. Some can vary. And the best way to explain, I actually explain it, I say, you are having meeting, 5 people are having meeting in the boardroom, and they have arranged 5 chairs for them. The first person go there, sit on the chair. If it's not comfortable, you can change chair. So the first person has choice from 5 chairs. Second person that comes has choice from 4 chairs, the remaining 4 chairs. The third person has choice from the remaining 3 chairs. The fourth person has choice from the remaining 2 chairs. The last person has no choice to vary, to decide which chair to sit. He can only sit on the remaining 1. So it's not the number of choices they have now. It's what we just want to illustrate here. Out of 5, because they have already fixed the number of shares, only 4 vary the share they see. The degree of freedom is 4. When the total of an entity is already fixed, all the entity cannot vary. All of them can vary except the last one, except 1. So that is why the degree of freedom is n minus. It's the entity minus 1. So sometimes when you say n minus 1, that one is only applicable to when you are talking of quantitative variable. So it's the entity, number of entity minus 1. If you are dealing with categorical variable, you don't use the total sample size. You use the number of categories, because you usually categorize. We say sex, male or female, 2 categories. So the degree of freedom for sex will be 2 minus 1, which is 1. If you say ethnicity, maybe there are 4 categories. The degree of freedom will be 3, 4 minus 1. But when it comes to quantitative variable, because you can have as many, you cannot count it unless you consider each of them have unlimited number of values. So the degree of freedom will be the sample size minus 1. So if you are now, maybe you are comparing 2 groups, or maybe you are comparing 2 variables, if the number of category of this variable, you are looking, maybe you are calculating cases where you are trying to consolidate 2 variables, both of them are categorical variables, the degree of freedom of 1 is, if there are 3 categories for 1 and 2 categories for the other one, the degree of freedom will be 2 minus 1, and you have to multiply for that particular thing. You want to multiply their degree of freedom. So 2 minus 1, 1, 3 minus 1, 2, 2 times 1, 2. So, but if it is quantitative variable, you are comparing mean, all this, what you do is for each of the group, you will remove 1, n minus 1 plus n minus 1. So that's just, so here now, what you just need here is, the degree of freedom here is the 5, n minus 1, which is 5. So when you divide that sum of square by the degree of freedom, that is the variance. That's why if you want to define variance, variance is the sum of mean square deviation from the mean, or you see average square deviation from the mean. If you will use the word average, you may not confuse people more. But if you say mean square deviation from the mean, mean square deviation from the mean, but you are talking about 2 means here. Mean square is one you get, that is by dividing this deviation from the mean by the degree of freedom, that is the mean. The other one, deviation from the mean, that is, this mean they are talking of, because this is deviation from the mean, square deviation from the mean. And you now define the average, the mean of that. That's why I say average square deviation from the mean. You say mean square deviation. Now, if you look at it, variance, let me tell you, mean and variance, they are the most, in fact, if they are not the most useful thing in the statistics, because in advanced statistics, that's all. Advanced statistics is all about this variance, mean and the variance, mean and the variance, mean and the variance. Advanced statistics. Anything statistically, it's around that mean and the variance. Now, why don't we quote variance most of the time? Because if you look at it, you have square. When you divide, the square element is still there. If let's say what you are measuring here now is in second, this variance will be in second square, because what you are measuring is in second. Maybe the unit is in second. The mean is in second also, because it is same, because the value, the unit of the mean is the unit of the original value, original data variable. But the unit of variance is the square, because you have done square here. So if the unit of the variable and the mean is second, this one will be second square. And if you want to quote, how will you quote? You quote center of measure of center tendency, use a unit, and you now quote center of measure of dispersion, use square. That is why, okay, what did you do with square? People, intelligent people, now let's find square root. So if you can't find the square root of variance, it gives you standard deviation. This is the variance. Can you see? X minus x bar square. The summation of all of them, that's the sum of square. Divided by n minus 1, which is the degree of freedom, that's the mean. I mean, this is the variance. But for you to calculate, if you now find the square root of that variance, it gives you the standard deviation. Because that standard deviation now have the same unit as the mean. That's why you quote mean plus or minus standard deviation. So calculating the standard deviation from the variance is like, after you have gone a step further, you retrace your step back. Since you square here, you will not find square root. Let me tell you something. If you are, let's say, under this deviation, if we neglect the sign, just add all of them together and divide by the standard degree of freedom, you will still get something close to this. You still get something, but of course, if you do that, you have opposed, you have undermined mathematical law. So that is why the best thing is to square it. When you are finished doing, you now find the square root back. It give you, so average. So the standard deviation is the average dispersion. That is average distance of each value from the mean. While the variance is the square of that average distance. Now you will see square root and variance and standard deviation is like water and ice block. If you want water, somebody give you ice block, let it melt. If you want ice block, they give you water, freeze it. So it's the same thing. So variance is square of standard deviation of square root of variance. I think it's very clear. We'll go back to where we are supposed to be. Does anybody have questions concerning it? Because you need the understanding of this variance, because everything about this Anova, and not only Anova, advanced statistics, even regression of this variance. Does anybody have any question concerning this variance I just explained? So we'll go to this, what we are doing. Any question? It's clear, right? Silence means clear. Okay? Great. I think we'll move further since no question. Now, so let's apply this principle, same principle of this variance now, to what we have. We have three groups. No, the variance I just explained just for one group, but just for us to get the understanding of it. Now, apply the principle to what we have here. They know that when you have more than one group, it's not only maybe three groups. When you have more than one group, the variance, there are three variances you can calculate. There are three variances you can calculate. You can calculate total variance, variance between, and variance within. And the total variance is addition of variance between and within. Now, if you remember, how did we calculate variance where we are coming from? We calculate variance by removing mean from each data set, and that is the deviation from the mean, and square it. When we square the deviation from the mean, we add it together, that will be sum of square, and divided by this degree of freedom, that is the variance. So when we look at total variance now for this data set, it will add all the 15 together, calculate the mean, and calculate the variance. This is the total variance, 3.124, the total variance here. And the variance in each group also is one level of variance within. This is the variance for group 1, group variance for group 2, variance for group 3. Can you see? So we have grand variance, total variance now, which is 3.124. We also have variance in each group, which is variance for each group. There is variance between groups that is hidden. How do you know the variance? You know, I told you the other time, even the grand mean, you can add the 2, 3 mean together and divide by 3 with the grand mean. So there is a variation, that is, each of these group mean differ from the grand mean. That they are different is the variance also. So if you can calculate, you can remove grand mean from each of the group mean and square it and calculate. You can calculate the variance. That will be variance between groups. So there are 3 variances now: total variance, variance within group, and variance between groups. Does anybody has any clarification on that? Because
Sir,
this, yes?
Thank you very much, sir, for this session.
Yeah.
So I understand that small. So it means the grand. So just to get just to confirm what you said, because you know there will be variation between the different groups and the grand mean, and that variance is the grand variance.
The difference between, what did you say? Repeat.
The grand mean, the
And
grand
what?
mean, and the individual group means.
Is it the individual group mean or
You said
individual
you made
value?
a statement. You said that is the difference between. No. You said the grand mean and the individual
Difference between
means.
the grand mean and individual value, that will be total variance. But the difference
Yes,
between the
I get
grand
that
mean,
one. Okay.
the grand mean,
Yes,
and
sir. I
the
understand
group
that
mean,
one.
each of the group mean, that is the variance between. There is the difference between the grand mean and the group mean. You know, each of the group has their mean. The difference between the grand mean and the group mean is the variance between. You read? And the variance. Can you see
Then
now?
within will now be
within will be the difference between the individual group mean and their group members. Yes, I mean now. In the difference between the group mean and the individual value in each group is the variance within. You need to clarify that. I don't know if anybody has problem understanding that. So we are talking of. So if you are to calculate, if you remember now from what I've explained about variance, for you to calculate variance, you have to first of all remove mean, the value, that is deviation from the mean, and square that deviation from the mean. When you square the deviation, that is, I now add it together, that is sum of square. It is the sum of square that you divide by the degree of freedom to give you the variance. And that is what we have explained here. This table you are seeing, look at serial number 1 to 15. Number 1 to 5 is the group 1. Can you see? The placebo group. Number 6 to 10 is the group 2, the low dose group. Number 11 to 15 is the high dose group. group 3. Can you see arrange now? So if you are looking at grand, before we even talk about invariant, let's talk about their sum of square. You know, the sum of square is what you, when you calculate the deviation, you square you add together. The sum of square before you divide by the degree of freedom to give you variance. That is sum of square. Now, this last two column is the one that talk about sum of square total, which is from the gram. It is if you want to calculate the gram variance now, all you need to do is the sum of square total. You divide by the degree of freedom, it will give you the gram variance. So this is sum of square total. How do you calculate it? Can you see the second to the last column? We remove the gram mean is the double bar. We use, you know, since we are having two levels of mean, the group mean and the gram mean. We now use bar X for the group mean and double bar X for the gram mean. Bar or bar X. So if you remove the gram mean from individual value, which is this second to the last column, you see now, and square it, it gives you sum of square total. Now, if you want, and this sum of square total is addition, when you add the sum of square within and sum of square between, you add up to sum of square. Let's look at sum of square between the group. So that one is this the two middle. If you look at this one now, you remove the gram mean from group mean. Can you see? The gram mean, if you remember, is 3.47, and the group mean for each of them 3.25. So if you look at it from 1 to 5, the first, when you remove 3.47 from 2.2, it gives you minus 1.27, because it's the same group mean for the first 5. You know, the first 5 belong to group 1. That is why you are getting the same value, minus 1.27. That is removing gram mean 3.7 from 2.2. Give you this. So for the next 5, which is number 6 to 10, which is group 2, you remove 3.2 from, you remove 3.47 from the 3.2, which is the group mean. It give you minus 0.27. That's why it's for the same thing for the 5 of them. Then the last group, which is 11 to 15, group 3, you remove 3.47, which is gram mean, from 5, which is the own group mean. It give you 1.52. That's what it is. But if you try to add it together, it gives you 0. So you square it, it gives you the sum of square between. So the sum of square between is by looking at difference between the gram mean and the group mean. While the total sum of square is looking at difference between the gram mean and individual value. Then the sum of square within these first two columns. For each of the group, like number 1 to 5 now, which is group 1, you remove their group mean 2.2 from each of these values, X. For group 2, which is 6 to 10, you remove their group mean 3.2 from each value, it gives you this. And for group 3, which is number 11 to 15, you remove their group mean, which is 5, from each value. When you square it, it gives you, and you add it together, it gives you 23.6, which is the sum of square within. If you add this sum of square within and the sum of square between, try and add it, it will be equal to the total sum of square. I want to entertain questions, because once you understand a number from this stage, chicken, the deed is done. So please don't hesitate to ask questions.
Now I know.
Or ask you questions.
You know, I kept on having this back and forth, especially when it comes to this particular. But now, it's now clear why it is within, because for that first part, it is each of the you're subtracting the group mean from each of the X. That is each of. That's why it is now within.
Yes, within. Yes.
Then for the between, you're using their actual group means.
Yes. You are removing gram mean
So
from
it now makes sense what is between each of them, because each of those groups have their group means.
exactly.
So you're now, it's not that it's now clear. If I know it had been something, I just say, I just want to thank you.
Okay.
Oh my
That's
God.
great. Any other question? No? No question. Okay, we proceed. Now, having done that, what you have done is to calculate sum of square within, between, and total sum of square. The F ratio you are calculating is actually the division of the variance between divided by variance within. No, we have said it. Between group variance divided by within group variance. Now, what we have calculated here is their sum of square. We have not calculated the variance. Because you calculated variance from sum of square by dividing the sum of square by the degree of freedom. So you don't need to calculate the total sum of square here, in total variance here, because we are not using the total sum variance does not contribute to calculation of F. Is variance between over variance within. So that is why we move the total sum of square between, which is 20.1335. We divide it by the degree of freedom. What is the degree of freedom for between? Because there are three groups. 3 minus 1 will be 2. And you see, so the degree of freedom for between is the number of group minus 1. J minus 1. There are 3 groups minus 1. So me SB just means sum of square between. Mean square between. Mean square. You know, this is sum of square. Mean square is variance. No, we say variance is mean square deviation. So when they say mean square, it's actually mean square deviation. They don't say it completely. Mean square means mean square deviation from the mean. You know, sum of square mean sum of square deviation from the mean. So mean square deviation is the variance. So this over standard degree of freedom, it gives us 10.06. Then if you want to know the mean square within, that is variance within, is sum of square within over the degree of freedom. The degree of freedom is 12 because each of the group, the within is calculated for each of the group, is from their mean from each value. So for group 1, the degree of freedom will be 5 minus 1, group 2, 5 minus 1, group 3, 5 minus 1, 4, 4, 4, 4 plus 4 plus 4, making 12. So when you divide this by 12, it gives you this variance thing. So the F ratio, which is your statistic, mean square between over mean, that is variance between over variance within. Simple. It gives you 5.11. If you go to statistic table, we are going to explain that later. There are 2 degrees of freedom you can see here now. You have the degree of freedom for between and for within. Both of them contribute to the F. So when you are looking at statistical table, there are 2 degrees of freedom. The numerator is the between. The denominator is the within. So I think, where did I put it? Where did I put that? Okay. Look at the statistical table. Right? If you look at it very well, numerator, what is the degree of freedom? Is 2, because there are 3 groups minus 1. 2. What is the degree of freedom for denominator? Is 12. Where does 2, the role of the 2, the column of the 2, and the role of 12 meet? Is 3.89. So the critical value for those 2 degrees of freedom is 3.89. And what we calculate is 5.119. Showing that statistically, because it's higher than the critical value. So we can run it. That's how to calculate. Very simple. This is one way another. It's very simple. So before we run it with SPSS, it's one of us that will run it. It's not me. Before we run it, any clarification? Any clarification?
Sorry, sir. So that means it's significant.
Yeah,
Since it
it's
is more than the
significant
critical
because it's
value.
that's so that the p-value will be less than 0.05. No, you cannot calculate the p-value.
You've explained it before to me that the critical value is at that point where it is, that point where you're ascertaining, oh yeah, this is where you're saying it to be significant. So once it goes above it,
if it's above it, that should that.
So what is it?
The
What's it? That
p-value
means
will
it has
be less
entered
than
into the
0.05.
significant zone. There was a way you explained it.
What do you say?
Now, so that there was a way you explained that critical value, that because it is more than it has entered into the significant zone. So it has gone beyond that 95.
Okay. Yes. Okay. The way I explained it, okay, maybe let me draw some.
Or you don't want to explain your own because that's the way I remember it. Okay.
When you draw, normal distribution is the basis for hypothesis test. This is 0 here, and the 5%, the middle 95%.
Yes.
This one is 2.5%. And 2.5% on the other side. That's significant level.
Yes,
so when you say your significant level is 5%, that shows that the error level that is will be outside the middle 95. So if what you now calculated is within this 95, if it's more than, if the critical level is high,
okay,
it will be within this zone. Yes, I'm now. No, sorry, it will be outside.
It's the other way.
Yeah, it will be outside. That is, it can be either from the extreme end or whatever. Once it's beyond that middle 95, it has entered the critical level. So if the value,
because I'm guessing that in this case, from that table we saw where we entered the difference, that is
okay. Let me
the degree of freedom. I remember that the critical value was 1.86. What that means that's like when you drew this curve, that mark where it's 0.05, if write 1.6 on that line, and because you're calculated 5 points, so 5 points will be ahead of 1 point.
Yes. What did I say? Look at.
That's why I'm just trying to rationalize it, to think it.
Okay, look at it here. This is the F distribution now, because it's not.
Okay, so when you draw the curve, exactly. So that point, that line we see,
yes,
is this critical value we found on this graph? I think the 1.86.
Just wait. It's increasing from 0 as it's going. Yes, I'm now. If the critical value for the degree of
freedom. So now let's say that the critical value is the line that this line your dot is on now. So you know that the calculated was 5 point something. That means to be above it. That is to be ahead of it. So yes. I guess that is why it is significant.
Yes, now it's ahead of it. So at the end of the day, it has this. The critical value is the bigger part. Yes, I'm now. As it's coming now, it has entered this zone. So that shows that if the critical value is above, if your calculated value is above critical value, that's why your P will be greater than 0.
It has entered
the significant zone.
Okay. Thank you, sir.
Okay. Any other question?
Thank you, sir.
Any other question? Any other question? No question. Okay. Now let's move further. Okay, who will run for us? Yes. Who will run it for us? Who will run it for us? It's not me that will run it to. It's Dr. Ebenezer. You have your this here. You open your SPSS. Open your SPSS.
I'm opening it now.
And open it you open it outside Zoom and now enter into Zoom and double. You see share. Let me allow you to. You see share.
That is Viagra.
Huh?
Is it Viagra?
Yes, it's Viagra, yes.
Is it Viagra I'm opening?
Yes, it's Viagra, yeah.
It's opening.
Yeah.
It's a bit slow, but it's opening.
Okay.
Exercise on patient. Still opening.
Okay.
Okay, it has opened now. How do I share?
Okay, come to the Zoom. Click on your Zoom now. You see where you see share screen. When you click on it, you now see the one you have opened. You now double click on what you have opened. Click on the share screen. When you click on share screen, it will show you many something. You just double click. Now double click on what you just opened. It will show up.
I'm still looking for share screen. I've not seen it. Which direction is it?
It's down. Are you in the Zoom? Have you come back to the Zoom?
I'm on the Zoom now.
You see it's green like this clear screen.
Stop video, participate, share screen. I've seen it now. So I should double click it. I've
click on it, but when you click on it, now double click on that thing you have opened. The SPSS you open. Double click on it.
I have double clicked it now.
It's coming.
I have clicked it.
We have seen it.
Okay.
We have seen it.
Okay.
We have seen it. So you see that. That's how to do it. You see that the dosage. Okay, go on view. There's a view beside edit. Click on it. Click on the view. Click on value label. Come down below grid line. Click on that value label. Can you see? It has labeled because the dose.
Placebo.
Those 111 is yes. 111 group 1 is placebo. Group 2 is low dose. Group 3 is high dose. The second column is the libido. If you look at it, because they are independent group, there are 3 separate groups. They are entered in series. In series means one after the other. After we enter the group 1, we now enter group 2, like that. Just forget about dummy 1, dummy 2. I created it there for regression. Now it's only the dose and libido you are using. Go to analyze.
Okay, so analyze.
Yes.
Okay, then compare
means go to one way Anova. Yes.
Then,
move libido.
Which one do I take?
Libido.
I should take libido to the independent group.
Yeah, to the dependent list, yes.
Okay, then dose to the factor.
Great. Click OK.
Then,
just leave that one. For now, we are coming back to just click OK. Okay.
Okay, we are not going into the other side. Okay, I should just click OK.
Yes.
Okay.
We'll come back to that one. Now, go back to second share. It will appear at the upper part, second share, and share your result because result is not showing.
I cannot see where second share is.
Oh, share second share is up. It's up. Go or is in the Zoom up. Go. You see up.
Okay, in the Zoom.
Yes, you see it now. You see if you put your cursor up. Okay, stop sharing then. If you stop sharing and go and share again. Stop sharing then.
My Zoom is minimized, so it's difficult for me to.
You are not supposed. No.
I should stop.
You see there's something. Stop sharing. Stop sharing. You see there's something. Stop sharing.
I've seen it. I should stop it.
Please stop sharing. So go back to the sharing now. If you go back to share screen now, you will now see the result. It's not, there are 2 windows. There's where in the SPSS where it give you the result. Go and click on that one. Yeah.
Okay, is the result you want me to?
Yes.
I thought you said I should start all over.
No, it's not starting all over. Just click on the
I
share.
am on it now. I am on it now.
So you want to click the data editor window. There is a result window. Okay, if you go, click on window, you see window up here. See window. Click on that window beside app. Click on the window. Click on it.
I clicked on window.
You will see output.
I'm on it.
Yes, you will see is check Viagra data statistic data editor. There is another one output number one. Click on that one.
Is it number 1 or 2?
Number 1.
I should click on number 1. Okay.
Yes. But you see, have to share it for us. Second share, share again. Go to second share. Is up. Look at up.
That is, I should go back to view. I should go back to window.
No window. In your Zoom where you are now. Up, go up. You see second share. Share again. Second share. You see second share.
My Zoom is minimized. I can't see second share.
Okay.
How do I expand this Zoom now?
No, it's stop sharing. It's you that you stop sharing. Stop sharing.
My
if
Zoom
you want
is
to share now, don't go and click on this other window. Go and click on the result. We are share again. But when you go, don't go and click on the other one. Click on the result.
On the result now.
Yes, the result, yes.
Okay, I'm on the result now.
Double click on the result. That's what we are saying. So that's shown us the result now. Everybody is seeing the result. You will see, can you see Anova, right?
Yes.
You will see between group, within group, total. Then you see sum of square. Can you see sum of square between? Can you see? That was what 20.133. That was what we calculated for our sum of square the other time. Between. Then you see within 23.6. Then total. Can you see 43.733? If you add these two together, give you the total. That is what we calculated before. This is the degree of freedom. If you remember, the degree of freedom for between is 2. 3 group minus 1, 2. The degree of freedom for within, we say is 12. Because each of the group is 5 minus 1, 5 minus 1, 5 minus 1, making 4 times 3, 12. And when you look at it, the total degree of freedom is 14. If you add all of them, they are 15 minus 1 is 14. So even the degree of freedom between and within, when you add it together, it gives you total degree of freedom. The mean square, MS, which is the variance. You remember when we divide this 20.133 by 2, it gives us this. When we divide this by 12, it gives us this. Then our F is when we divide this mean square, which is variance between groups, divided by variance within groups, give us 5.119. That is what we calculated. The only thing we could not calculate is the p-value. The computer has given us. P-value is 0.025. Is it significant or not?
It's significant.
Yes, significant. So that is how to run one way Anova. It's very simple. Stop sharing. Let's entertain question before we move further. Any question from any angle? Is it so? It's simple, right? No question. No question. Okay. Dr. Olagundoyin. I want to be sure that all of us are here.
Yes, sir. Hello.
Yes, no question.
I'm here. I'm here. The SPSS version 25 for me is not working because of the license. No. Asking me for the license, I can't. Even though I've downloaded the files that Dr. Gonaya sent, but they are not open because it keeps asking for the license.
No.
So I think I'm going to find a way of going back to my version 20 or something, my old laptop, to see if that will work. against tomorrow.
Oh, have you finished? No, have you finished? You finished installing it, but there's no like you.
Yes, I have.
Have you finished?
Yes, I've finished.
You have finished installing it.
Yes, sir.
Okay. You know what? Go to the side where you usually open your what do I call it? Okay. The folder. Go to that file. The folder. There is something that has. I'm trying to.
One of the Viagra file.
The
Any of the 6 files.
SPSS folder you want you install.
Okay.
Once you are finished installing now, go to the file. There is one file there that before the main file.
Yes, there's a file.
There is one that they wrote 3 something. Wait.
Yes. Recently used data, recently used files, exit, collect variable information.
No, there's something I want to show. You cannot minimize with okay. There's something I want to show. I want to show you. I forgot the name. Let me look for it on my desktop. Because there's something you just need to put a code. It will work. It's a code you just need to put. It will work.
So maybe I should not disturb the class with that. I can.
Okay, no problem. Later we'll do it. Later we'll do it. What the question I'm even asking? Any question? Are you following?
Yes, I'm following, sir.
Okay, Dr. Balogun. Go on. The what? Hello? You have to unmute yourself. I'm not hearing you. Okay. Okay, no problem. Let me just. Yes. Now, this is the result we have seen. Then, we want to ask. This is the output we just did this now. Though the only thing we didn't click on descriptive. This is descriptive. We have click on descriptive. It will show us all these. They are the mean for each group, the standard deviation, and also give us the confidence interval of the mean, minimum, and maximum. This is the other one that Dr. Kobo showed. Now, come and see. If you are to write the formula of the F-test now, you will see that the F-test is the ratio of the mean square among the group, which is mean square mean variance among the group divided by the mean square within the group. Now, if you look at the mean square between the group is x bar minus s double bar, that is the sum of the group mean minus the gram mean over degree of freedom square over degree of freedom, which is j minus 1, number of group minus 1. Then for within group mean variance is summation of x minus s bar, that is each individual value minus the group mean square all over the sum of the degree of freedom of all the group. So the F ratio will be all this over this. So you look at it, you don't even need to cram any formula. You get to understand it. Now, let's quickly talk about F distribution. You wonder, why should I first of all explain the logic of F ratio before I talk about F distribution? It's because the F distribution, the F ratio or F distribution is not only for Anova. It's not only for Anova. It's not only for Anova. Comparing two variances, even you can use it to test equality of two variances. So let's quickly look at F distribution. F distribution is the probability of F. It is the probability distribution of F. It is the distribution of all possible value of F statistics. If you remember when we talk about probability distribution, is the distribution of all the possible value of a variable and their probability. That is the probability distribution. All the possible values, the list of all the possible values of a particular variable, and their probability. That's probability distribution. So F distribution is a form of continuous probability distribution, just like normal distribution, T distribution, chi-square distribution. They are all continuous probability distribution. Why? Because those continuous probability distribution, it is not possible for you to know all the possible values. But for discrete probability distribution, you can know all the possible values. So you can only, for discrete probability distribution, you can have a table where you list all their values because you can know all the possible values. You list their value and the possible and the probabilities. That's for discrete probability distribution. But continuous probability distribution, because it is difficult, you cannot actually know all the possible values. So you cannot have a table where you list them, but you can represent them by a graph called probability test function. Now, this is the probability density function of F distribution. There are some things you want to know about F. It is a family of distribution, just like T distribution, chi-square distribution, because they are family. You know why they are family? You don't have only one distribution, because you have different distribution for different degree of freedom. So it's only in the normal, standard normal distribution that's only one. That doesn't depend on degree of freedom. But all these other distributions, T test, chi-square, F distribution, they are family of distribution in the sense that the shape of the distribution depends on the degree of freedom. Now, you will see, okay, that one, now, F distribution have it in common with chi-square and T distribution. But there are some things F distribution make F distribution to be different or to be different from chi-square distribution and T distribution. One major is the degree of freedom. You have 2 degrees of freedom for F. For a particular curve for T test, there is only 1 degree of freedom for a particular curve. For T test, for chi-square, it's only 1. But for F distribution, there are 2 degrees of freedom. And it's a pair of so the degree of freedom for numerator and for denominator. And that is what we explain when we're calculating the F ratio. So if you look at all these graphs, you can see 2 degrees of freedom for each graph. These are their value they put in bracket. You are seeing. For this one, 2 degrees of freedom for each graph. Now, then just like chi-square distribution also, you see the shape of the F distribution is skewed to the right. It varies from 0 to infinity. F distribution, look at, let me explain it from the characteristics of F distribution. The curve is not symmetrical, but skewed to the right. It's not symmetrical like normal distribution or T distribution, because T distribution and normal, they are symmetrical. The chi-square and F distribution, they are skewed to the right. The reason means that they don't have negative. They are range from 0 to infinity. They don't have negative value. If you look at T test, T distribution and normal distribution, they have negative, they have positive. The 0 is in the middle. The negative side is a mirror image of positive side. Those are the characteristics of normal distribution and T. But for F and chi-square, you know, people that were around when we talk about chi-square was actually originated from normal distribution, because you square normal distribution. When you square it, you know, normal distribution, there are some values that are negative. All of them turn to positive. So it's going to be from, so the value of chi-square ranging from 0 to infinity. It's the same thing with F distribution. It's from 0 to infinity. There's no negative value. And that's why it's positively skewed like chi-square. In fact, there is something mathematically, F distribution is division, is a ratio of 2 chi-square. 1 chi-square as denominator, chi-square as numerator, denominator. That shows that the first variance follow, maybe the first variance follow chi-square, the other one follow chi-square. Now, F statistics is greater than or equal to 0, I've said it. Then there's something that also makes F distribution that it has in common with chi-square and t-test, T distribution. As the degree of freedom increases, the distribution approaches normality. As the degree of freedom of F distribution increases, the distribution looks like normal distribution. Look at it. Can you see? Look at different degree of freedom. This blue one, the first blue one is, can you see the degree of freedom? The other one, as the degree of freedom increases, look at the last one, the red. It looks like normal distribution. When the degree of freedom on both numerator and denominator side increases, the F looks like normal distribution. I don't know if you have any question concerning F distribution. Now, the F distribution is used in many cases for critical rigor for hypothesis test and determining confidence. 2 common examples, Anova, which is what we just described, and F test to determine if variance of the population. So you see, the F is not only for Anova. You can only use it to compare 2 population variance by dividing one by the other. Of course, if both of them are equal, you expect F to be 1. If it's not too far from 1, that shows that both of them are equal. But if the value is far from 1, that shows that the 2 variances are not equal. That's the logic. So F is about division of 2 variances, comparison of 2 variances. After all, we have established the fact when we're looking at the logic of Anova that F Anova is variance between divided by variance. I don't know. I shown all the critical value. Because there are 2. Okay, Hugo, ask your question. Hugo, unmute yourself and ask your question.
Okay, thank you, sir, for the. So it was there was something you mentioned. You talked about the SS and Anova being different. That is, so I was trying to understand that part about SS and Anova. Because I know for the Anova, we're dividing the mean sum of squares between divide over the mean sum of squares. Can you hear me, sir?
I will hear you.
Is it clear, sir?
It's clear, yes, I'm hearing you.
Yeah, because we're dividing the mean sum of squares between divided by the mean sum of squares within.
Yes.
So I thought that was I thought that was the same because that's still the F ratio. So what's the difference between the F test and then the?
Yes, the other one also.
And I thought the F ratio was linked to Anova.
If I'm telling you, I say the F ratio is not only for Anova. Anova is not only for Anova. F ratio just means you are dividing ratio of 2 variances. So if they have, you have 2 groups now. Yes, just ratio of 2 variances. If you have 2 groups, you want to see if the 2 groups are the same. So you divide them. If you divide them, if they are the same, it will be equal to 1. Or if we vary from 1, it will be slightly small. But if it's far different from 1, either it's far less than 1 or far greater than 1, that shows that the variance in the 2 things you divide are not the same. You get the picture now. So we are dividing 2 variances of 2 is F ratio also. But the one for Anova is variance between over variance between. Yeah, just guide the logic. Do you get it now?
Okay. So the F test is the name of the statistic.
Yes.
Yes, sir.
Yes.
Okay, now understand. Okay, thank you.
Okay, thank you. Any other one? Any other comments?
Can you repeat what you said about the confidence interval, its interpretation in relation to F statistics?
Okay, what I just said. I say F. The two common example of using F are F test and Anova. F test in this sense is to determine if variances of two populations are equal. So it will divide one variance by the other one. Of course, if they are equal, it should be 1 or not too far from 1. If two things are equal, you divide one by the other, it will give you 1. That is the F test used to compare two variances. Anova also is two variances you are comparing, but this one is a special case now where the numerator is the variance between and the denominator is variance within. So what I just say here is just for you to, when you are comparing two variances, whichever way, either Anova or F test, is helping you to test the difference between two variants. That's all. And their confidence interval. That's what I just said. It's just like the way we tell difference between mean and their confidence interval. Because if you want to test if two means variances are the same, what will happen is that it may not exactly be 1 even if they are the same. If they are not the same, it will be either less than 1 or greater than 1. If their confidence interval now crosses 1, of course you know that that shows that it's still the same. There's no difference in the two variances. That's the realm of F test. We are not even discussing F test now. That is why I decided to discuss F distribution after I've given the logic of F ratio, because what we are interested in here is comparing more than 3, and that is the Anova. So what I'm saying that their F ratio is not only for Anova. It's for Anova. They also use it to compare two variances. That's what I said. Any other one? Any other one? Should we proceed?
Yes, sir. Would we now say that a higher degree of freedom correlates with a higher variance?
A degree of freedom. Why would you say that?
A higher degree of freedom, because you talked about the higher the degree of freedom, the closer it is to a normal distribution curve, which means that if the F distribution curve is correlating
what
with...
was now your question? Now you say the higher degree of freedom mean what?
Now I say that the higher the degree of freedom, the closer it is to the normal distribution curve.
Yes, that's what I said. Yes.
So my question is that, does it mean that the higher the degree of freedom, the higher the variance that's
no, it doesn't say.
That
has nothing has to do with the higher degree of freedom doesn't mean the higher the variance. You get the picture.
Okay, that's true.
Freedom just show is that
yes,
if
that's true. Yes,
when the degree of freedom both are both numerator and denominator increasing, the distribution look like normal distribution. Oh, just say it's close. Just like even the
I was just trying to understand
if the degree of freedom increases also with chi-square, it look like normal distribution. If the degree of freedom increases with T distribution, it look like normal distribution. So F distribution also share the same bias with them. As the degree of freedom increases, they look more like normal distribution.
Okay.
Yeah. Shall we proceed?
Okay, I think I understand. I think I now get it. It's more like when you're having a larger sample size. When you're having increased sample size, it gets you closer to your
normal distribution. Exactly.
I now understand it. I was trying to understand the logic. Once I understand the underlying logic, I now understand. Okay, thank you, sir.
Yeah, you're welcome.
Yes, now, exactly. That makes sense.
Let's now talk about post-hoc test and plan contrast. Now, the question, yes? You want to charge it? So, and don't worry, I'm using this one, it's okay. Now, if after you have done your test, Anova, if there's no significant difference anywhere, you rest your case, no difference anywhere. That's the end of the test. But if there's a difference, where does the difference lie? Like this example we have just done now, where is the difference? Who knows where the difference lies? We have 3 groups. And these three groups, you can pair them in three ways. Placebo can be paired with low dose. Placebo can be paired with high dose, that's second. Low dose can be paired with high dose, that's third. So where is the difference? The difference we have found now, we found that it's statistically significant. Can we categorically say that, oh, the libido between, there's a different libido between the people that took placebo and low dose, and between the people that took placebo and high dose, and the people that took low dose and high dose? Can we say it? We don't know. Can we say it, or it's only one of them? That's true. So for you to find out, you have to move further. And there are two ways to do it. You either use what's called planned contrast or planned comparison or post hoc test. The planned comparison is more useful when you have an hypothesis in mind. What I mean by that's why they say plan. Hypothesis means that you already have a clue about the group you have studied that, oh, it's likely that this one will be higher than this. No, you have an hypothesis in mind that, oh, one may be lower than this. It makes sense. With that, you'll be able to do your plan contrast. But if you don't have, you cannot really say, these 3 or 4 groups, we cannot even see. There's no justification to say that this group should be higher than this group. So in that case, it's easier to do post-hoc tests. Let's quickly look at the plan contrast. The post-hoc test is even more straightforward. Let's first of all look at the plan contrast. What I'm saying about plan contrast will be clearer as we look at it and look at the picture that follows. What's the meaning of contrast? Contrast just means comparison. It's a linear combination of 2 or more factor level means with coefficient that sum to 0. That one, if I'm to explain it, may waste time, but you will get to understand it. If it is time, maybe I will even remove this 2 side. Let's just go straight to the diagram. You understand what plan contrast means. Now, to explain what contrast means, we still start with what Anova does. If you remember what we have just finished doing with the data we have now in explaining Anova. The Anova, what it does is to split the variation or variability or variance into 2. The variance between and variance within. It split the total variance into between and within, and now divide the between by within. So if you remember, the total variance is this. Then it's divided into within and between. The within is the model. We call model. I don't know, I will have maybe go and change this. We were confusing. So the residual is the within. The word model and residual is used, more in regression because Anova and regression is the same. You get to know that one later. So the sum of square between, which is the model, which is the systematic variation, and the sum of square within, which is the residual, which is unsystematic variation. That is what Anova does. It split them to 2 and now divide this by this. We use our video data. If you look at the total sum of square is 43.73, split into 2, explained by the model is 20.13, non-explained by the unexplained variance. The one that your model could not explain is 23.6. That is what Anova did. But the plan contrast now took that approach further. The plan contrast, after Anova has found a difference, but it doesn't know where the difference lies. The plan contrast now go further by splitting the model, that sum of square between, into the different groups. Split it into the different groups. So the sum of square between now, if you look at for this, our Viagra data is 20.13. So you now split it. You now plan comparison, what it means that you plan it. You still combine them as if they are 2, 2, 2. But not that you are pairing them. Combining them as 2 does not mean that you are pairing. So the first comparison you do, all of them are still involved in it. That shows that if you want to compare as if you are doing 2, it's like t-test. It's actually t-test you are doing. You collapse. If there are 3 groups, you collapse 2 groups and compare with 1 group. The second step, the 2 groups you collapse before, you now split it and compare it. Can you see? You are comparing them in stages. So the first step will be contrast 1, comparison 1. Second step will be contrast 2, that is comparison 2. So the implication of that is that when you have 3 groups, you can only do 2 contrasts. If you have 4 groups, you can only do 3 contrasts. If you have 5 groups, you do 4 contrasts. So look at it this now. We have 3 groups now. The first contrast is to collapse 2 groups and compare with 1. The second contrast, that one that stood out in first contrast is out of the game. So these other 2 groups you combine. That's why you split to compare in the second contrast. Now, what informs you which one to collapse? That's why they call it plan comparison. That's why they say you must have had some hypothesis in mind for you to know how to do your plan contrast. Now, to make what makes sense here, when you have 3 groups, one is placebo, one is low dose, low dosage. Second, in another one, the third one, high dosage. It makes sense for you to collapse the low dosage and high dosage and compare with placebo, because either low or high, at least they took drug, while the placebo did not take anything. So can you see is the logic? So you make the decision to first of all combine the low and the high, and now compare the effect with that of placebo. That will be contrast 1, first contrast. Your contrast 2, the second contrast will now be, you now split that low and high and compare the 2 together. That's the logic. Now, if let's say, other thing I'm trying to show here, it will give you an example of 3 groups, in 4 groups rather. Let's say you have 4 groups. These 4 groups, we have 3 of them experimental, 1 control. It will make sense for you to collapse all the 3 experimental and compare with 1 control first, which is the first contrast. The second contrast is now those 3 experimental you collapse, you separate 1 from it and compare with the other 2 combined. That will be second contrast. The last contrast will be that last 2 you combine, you now split them and compare the 2. So you can see there are 4 groups now, but you did 3 contrasts. But another approach to do contrast with 4 groups is this. It's still 3 contrasts, but another approach. Imagine the 4 groups are 2 of them experimental, 2 control. So you can collapse the 2 experimental and collapse the 2 control and compare. That will be first contrast. The second contrast is you now separate the 2 experimental. Okay? The third contrast will now separate the 2 control. So it's just another approach to handling 4 groups. But eventually, whichever way you are doing 3 contrasts. So when you have 4 groups, you do 3 contrasts. When you have 3 groups, you do 2 contrasts. So the number of contrasts is the number of groups minus 1. Now, this contrast, what does it mean? How you define it? This contrast is by giving weight. Before I talk about the rule, let me just show you how, for example, for this diagram, how do we give weight, assign weight to this example we have used. Look at the first contrast. Know there are 3 groups. You know that we're going to do 2 contrasts. The first contrast will be, okay, you combine low dose and high dose, compare with placebo. Then the second contrast, the placebo is out. You compare the low dose and high dose. Now, what you do is you assign weight. The weight must be equal and opposite on both sides. Now you are comparing low dose and high dose together against placebo. The simplest weight you can assign is 1. You cannot assign anything less than 1. If you give low dose 1, high dose 1, then because you are comparing it with placebo, you have to give placebo 2 because it must be minus 2. If this one is plus, this one is 1. Unless this placebo can probably be plus, if this one you assign minus, it can be. So if you have assigned 1, 1, yeah, this one will be minus 2. Number, you see now, if you had the two opposite sides together, it will give you 0. Now, when you are done with that, the second contrast, placebo is out, the low dose and high dose. You must, number 1, the placebo, since it's not participating, you assign it 0. And now, when you now come to this, when you now come to minus and plus, the low dose and high dose, you give one minus and give them one plus, just to cancel that when you add them together, it still gives you 0. Now, let's look at the rule. I will be oscillating between the two slides. When we go through the rule for assigning contrast, it may give you some better understanding. Okay, for example, number 1, choose sensitive comparison. If a group is sensitive comparison here just means that if you are choosing a contrast, for example, it does not make sense for you to go and choose you want to do first contrast. You now say you're collapsing low dose and placebo. You are comparing with high dose. But it makes more sense to say, okay, low dose and high dose, those ones they are taking drug, even though the dosage are not the same. But you are comparing with those people that didn't take drug. So it depends. Another person may decide, okay, I'm combining, you may say you want to combine low dose and placebo and compare with high dose. But to me, it doesn't make sense. So can you see how you compare your contrast? It depends on the way your hypothesis is, that the way you look at which one should be greater, which one should be different from which one look more similar. So your comparison should be sensible. Right? If a group is single out in one comparison, that group should be excluded in the subsequent one. Look at it. Look at the first contrast. We single out placebo. We combine high dose and low dose. So in the next contrast, placebo is out of it. If those ones that you combine, you want to split to down do the contrast. So that is the rule 1. When you single out a group, that group is out in the subsequent one. That's rule 1. Rule 2, group coded with positive weight will be compared against group coded with negative weight. Look at it. If you look at it, the low dose and high dose in the first contrast are coded with positive weight. You are comparing it with one that are coded with negative weight. Can you see? Can you see? You give positive, this one must be negative. And so the sign you give here must be negative. If the sign, the other one is positive. Can you see? Now, rule 3, the sum of the weight for a comparison should be 0. Can you see? Sorry. In each of them, if you had all these for contrast 1, this comparison, the sum is 0 because as much positive you have negative. So when you sum it together, it should be equal 0. That is that. Then 4, if a group is not involved in comparison, automatically that group carry weight 0. Look at it. If you look at in contrast 2, because we have singled out placebo in contrast 1, it's no more part, it's not involved in the comparison. So that's why you assign it 0. Assign it 0. Does it make sense now? Now, the last one. For a given contract, the weight assigned to the group, the one chunk of variation to be equal to the number of group in the opposition. What this one is saying that way? What is it? The way you assign, look at it. You assign 1. Okay, let's start with this. You assign 2 to placebo. Because there are 2 groups opposite facing it. That's why you are giving it 2 groups. You assign 1, 1 for each because it's one group that is facing them. Look at this one here now. 1, 1. Is one facing this one? One is one facing this one. So the weight you assign to a group is the number correspond to the number of the group facing opposing that group. Now, maybe I don't know. Before I talk about something orthogonality, is there any question concerning what I just explained about contrast? Any question?
Sorry, sir. I just have one quick one.
Okay.
In the one we talked about the group experiments, you know, you talked about plan contrast, talked about how you had the systematic variance, which is the between, and the unsystematic variance, which is the within. That's the one that is split. I noticed that in that group experiment, we had 3 experimental groups. We had the control group, and under all of them, they were under systematic. I guess
Oh,
because
forget it. Okay. I think we
that's
need to
an
clarify.
elemental
Okay, no worry.
manipulation.
We need to clarify something. The word, it's just like the way you use the word experiment in research. It's different from experiment in laboratory. When you say experimental design, it means you intervene, you do something. So the word experiment in research is different from experiment in the lab. And the funniest thing, even the word experiment in research generally is different from the word experiment in probability. Yeah. Now, what I just want you to see here is that when we talk about systematic variance here, it's talking of the variance. When we talk about systematic, it's talking of the group you are looking at. The group may be experimental group or control, it doesn't matter. It's just talking of all the group you are looking at. Do you get the picture now? The unsystematic variation is the one you cannot even explain by your study cannot explain it. You examine that. That is the unsystematic. So when we are talking of systematic, even if it is experimental research, experimental group,
that's your slide, like this one.
Yes, all of them, they are under it. Do you get the picture now? All of them, they are under, all the 4 groups, they are under that variant explained by the experiment. Can you see now? Variant explained by the experiment. Can you see? It says the experimental group.
Yes.
Do you get the picture now? So, and it gets a word. Even you can use the same thing for observational research. It doesn't have to be experimental research. It's just talking of data explained by the group you are studying.
Oh, I see. Okay.
Yes,
it doesn't mean it is for the systematic variance.
Exactly. It's for when they talk about
I understand
systematic variance, the group you are studying. Unsystematic is the one is not part of your. That's all you are trying to. The effect is all you're going to remove. It's not part of what you don't even know anything about it. You know, it's just like if you are doing research now, you do extensive literature. Doesn't mean that you have exhausted.
Yes.
All the factors that may be responsible for that thing. You may not. But you have just done extensive literature. In fact, there are some other factors you may not even know. It's later people will discover this one affect this. So, but as a systematic variance, not talking of what your research is catering for, the group defined by your research. It doesn't really matter either experimental group or control group or whatever you call them. They are under this thing. Does it make sense?
Yes. So because I guess because you had always said they were step, like that is, the what you taught us was I understand this one. So like in this case now, you're saying that's only the way you're now at the comparison level that you now have the systematic and the unsystematic. Where you're now comparing them.
Wait. If you remember, I said this slide is not about contrast. Though I wanted to explain, I say the logic of and I say notice that Anova is based upon splitting total duration into 2 components. It's systematic and non-systematic.
Oh.
Then I say that the plan contrast take the logic step
it's
further
different
by
from the
breaking
plan
down
contrast.
And I say the plan contrast take the logic a step further by breaking down the systematic variation due to experiment manipulation into component parts.
Thank you for this.
All your group. Forget whether you call it experimental or control group. All the group you are studying is under the model explained by the model. Does it make sense?
Okay. Okay. That's clear now. Okay. Understand.
What do I call it? The Anova has already told you, okay, the systematic variance, which is the numerator, is far bigger than the denominator now. It's significant. Now you now want to break down that
find out where the difference is. So you now split that between group to find out where in that point the difference is.
Yes, mechanism, how they are within the group you are studying. It doesn't really matter whether you call them experimental group or control group. All the group you are studying, they are under the model because they are under your explanation. Does it make sense now?
Excuse me, sir.
Yes, ma'am.
Yes, it does. Thank you so much, sir.
Okay. Go on, ma'am.
Is it logical to simply say that the systematic variance or the between group variation and the unsystematic variance, that's the within group variation, if I'm still on point, is it logical to say that within group can be like the individual differences that you cannot account for?
Yes, sir. Yes,
that would within the participants.
Exactly. Individual differences you cannot account for. And possible also there are maybe some factors you didn't study. You didn't take into your study. Either individual differences and other factor you don't even know. Your study cannot account for. Yes, that's what it means.
So somehow they can also be equated to like what will be your standard error or something like that.
Oh, great. You are right. You are right. That is the yes, it can be the standard error. You know, the standard error is it also show variability within in the population within the people. So you are right. If you remember, it's the same logic when we do t-test. The denominator is the standard error. It's the same thing.
Yes.
The denominator is the standard error. Because if the standard error is so big, the denominator is so big, it can offset even and so big that it even offset the difference you say you are seeing between groups. You can't say there's a statistical significant difference. Even the difference you are seeing it could look like this. If the denominator is so big, it will make your statistic to come down because the inherent variability, which may be the standard error, maybe the variability within the group, each of them may actually offset the difference you are looking at. No, I usually give an example. I say that imagine if you say the blood sugar among female is 65, average blood sugar, and among male is 60. Say, oh, someone can just conclude, oh, the women they have more blood sugar, higher blood sugar than men. But the issue there is that even among the men, that the average is lower than the female. Some have more than some female. Some even have more than the average for the female. It's just that the average you say, when you calculate the average for it, it's just that value. Some among them that are variable, some have extremely high blood sugar. And the women, you say that average is higher than men. There are some even women that have extremely low, among them that have extremely low value. Can you see now? So you see that there are some inherent variability. If the variability is much more than the difference you're looking at, you cannot say that difference is significant. That is the logic of the statistical test. Is it clear, Amma?
Yes, thank you, sir.
You're welcome. Now, let me quickly explain this contrast further. The contrast is the way you assign. Contrast is actually the way you assign weight to group to be able to compare them. So, and you start with the smallest one. You give 1, 1, 2, 3, 4. You be giving like that. You give. If sometimes if you enter data into SPSS, if you code, you don't code very well. Maybe you didn't code from 1. If you code 3, 4, 5, the lowest is 3. The SPSS will assume that 3 to be 1. You take it as 1. So that is why it's good when you are coding, you code from 1. If there are 4 groups, it will be 1, 2, 3, 4. If there are 6 groups, 1, 2, 3, 4 to 6. If there are 2 groups, 1, 2. These are 3 groups, 1, 2, 3. So now there are 2 types of this contrast. You can have orthogonal and non-orthogonal. Let me explain the word orthogonal. Orthogonality, what it means is perpendicularity. In vector, in mathematics, 2 vectors are orthogonal when they are perpendicular. That is, at right angle to one another. When something is flat, another one that come right, that is perpendicular. So those 2 vectors, if you multiply the 2 components of 2 vectors that are perpendicular, it gives you 0. So when you multiply the weight of a particular group in the contrast now, the contrast you give to a particular group, the product should be up to 0 if okay, for a particular contrast, when you add them together, it will give you 0. When you multiply the contrast for a particular group and the product, when you now do for all the group, and you now add everything together, is 0. That's orthogonal contrast. For example, I illustrated 2 of them, both orthogonal and not orthogonal on this table. The contrast we use for this diagram is orthogonal. Look at it. For placebo, if you remember the first contrast, the value of placebo is -2. And the second contrast is 0. Look at it. First contrast is -2, second contrast is 0. When you multiply them, it gives you 0. Contrast 1 times contrast 2, 0. For low dose, it's 1 and -1. For first contrast, low dose is 1, and second contrast is -1. You see. When you multiply, it gives you -1. For high dose, the first contrast was 1 and the second was 1. When you multiply, it gives you 1. When you now add all of them together, it gives you 0. If you add the 2 contrasts together, contrast 2 together, it gives you 0. Add contrast 1 together, is 0. Addition of the, we have already said addition of the 2 or all the contrasts for a particular should be 0. Contrast 1, 0. Contrast 2 is 0. If you multiply the contrast for each, the 2 contrasts for each of the group, the addition also will be 0. That is orthogonal. But for non-orthogonal contrast, it's not like that. If you look at it now, but within the contrast we use for this thing is not orthogonal. It's orthogonal we use for our Viagra data. It's not non-orthogonal. If for non-orthogonal, if you do it, you cannot add up to 0. Then there are some standard contrasts. When you say standard, there are standard way of coding. And SPSS, some of these people that do the software, they put them into their software also. So as I've explained, software SPSS give 1, 2, 3, 4. So if you don't even code very well, the lowest value is assumed is 1. So look at the way the standard contrast that people use. There are 2 types here, non-orthogonal and orthogonal. And we give example for 3 group and 4 group. You cannot have contrast for 2 group because 2 group you can only combine them in one way. You can only pair 2 group in one way. So it's only 3 group you can pair in 3 ways. 4 group you can pair in 6 ways. But the contrast, I said that the number of group minus 1 is the number of contrasts you do. Now, look at this one and 3 group. You can only have 2 contrasts. 1, 2, 3. It's only 2 that are applicable to contrast. So it's the group for 3 group. Is the group 4 group that the 3 is applicable, 3 contrasts are applicable to. Now, let me explain orthogonal contrast because it's easier to understand. The example of, there are 2 examples, Helmut and different. The one we use for this placebo is Helmut. What does this say? Each category except the last is compared to the main effect of all subsequent categories. Look at it. What we did was placebo was our group 1. We combine group 2 and 3 and compare with placebo. That first contrast 1. Contrast 2, we now separate the 2 and 3 and compare. If it is 4 group you are dealing with, that should have just like the way that one I show. Group 1, you combine 2 and 3 together, you compare versus 2 and 3 together, 2, 3, 4 together. Then the second contrast will be 2. No, 1 is out. You remove these 2, you compare with 3 and 4. Then the last one, you now compare 3 and 4. That is orthogonal. Is an example is MAT. That's exactly what we use for the diagram. The opposite of the MAT, which is the orthogonal way. Instead of you shooting first like that, you start from the last. Each of the category except the first is compared to the mean effect of the previous category. Look at it. Compare group 3, collapse, you combine 2 and 1, then later you now separate 2 and 1 and compare. So if let's say in our Viagra data, we say we compare high dose with combination of low dose and placebo first, that would be orthogonal different. And now later split the low dose and other group 1 and 2 and now compare. That would be orthogonal different. But what we use orthogonal elements. Now let's come to non-orthogonal. The non-orthogonal is very simple also. We have deviation first, deviation last. What is that deviation first? Very simple. Compare the effect of each category except last or except first to the overall experimental effect. Look at what they do. They remove the second one and now collapse everything and come. You remove the second one, you now compare with all of them. You now remove the third one, compare with all of them. In our example, now let's say we just remove low dose and now compare with all of them combined together, and also remove high dose and now compare with all of them. That would be deviation first. Deviation last is the opposite of that. Compare the effect of each category except the last to the overall experimental effect. Like you say 1 versus all of them, 2 versus all of them. Can you see? It's only 3. The last one you didn't use. You know, in the first one is only the first one you didn't use to compare with all of them. But here is the last one you didn't use. That's deviation last. We have simple first. Each category is compared to the first category. Like you just say 1 versus 2, 1 versus 3. Simple last. Each category is compared with the last category. You just say 3 versus 1, 3 versus 2. Then repeated. Each category except the first is compared to the previous category. Look at what they do in repeated. You say 1 versus 2, 2 versus 3. This one is useful when you get to repeated measure. When the observation taken is from the same group of people, you take measurement more than 2 times, 3 times, or 4 times. So that's why you use this repeated. Any comment? Then the last thing I want to say about this contrast here, there's one I didn't just show on that table, polynomial contrast. In a situation where the independent variable is ordinal, like for example now, even this example we use is ordinal because the example of diagram, placebo, low dose, high dose, is ordinal now. It's one that take nothing, low dose and high dose. It's ordinal. The dose is dose related, it's ordinal. So you want to see, is there any linear relation? Is there as you move along the variable, the independent variable, the exposure variable. So is there any increase or decrease in the mean what you are finding? Does it change? You're like for this case now, we expect the libido to be higher in low dose than placebo and higher in high dose than low dose. So we expect it degraded. That is linear. That's polynomial contrast. Sometimes it may not be linear. It may be increasing in our turn one time. That is quadratic. Either it's increasing in turn one time or it decreasing in turn one time. That's quadratic. If it turn 2 times, that's cubic. If it turn 3 times, that's quadratic. Then calculating value of contrast. What you do is that by the time you know what the weight you give is called coefficient. All this way you give -2 plus 1 is called coefficient. But when you are running it, how do you calculate the value itself? You just multiply the coefficient by the mean of the group. Like for this one, a placebo group, 2.2 is the mean, low dose 3.2 is the mean, high dose 5.2. So for contrast 1 now, the value will be you multiply this, the contrast by the mean, it gives you the value. So we now add it together. You know, this one will be 2.2 times -2 will be -4.4. This one 3.2, 3.5. When you add it together, it gives 3.8. So the value of the contrast for contrast 1 is 3.8. For contrast 2, you know, the placebo was 0. Yeah. So when you multiply 0 by 2.2 is given 0. Then the low dose was -1 contrast 2. Multiply by 3.2 give -3.2. Then the high dose was 1 contrast 2. When you multiply, it gives you 5. When you add it together, it gives you 1.3. So the value of contrast 1 is 3.8. Value of contrast 2 is 8. So I think somebody, let's go and run it now. Let's go and do it. Any question before we run? Any question with the contrast issue? Before we go and run it, next verses.
This is just more of a comment. I think in plant contrast, what determines what to run sometimes is the way you plan your experiment or study.
Yes, yes.
Because there is no standard rule. But what I've been trying to struggle to understand is that if you take the control out and you are left with maybe 3 groups, and then the next one, you are comparing 1 to 2 plus 3, and the next one you take 2 and you are comparing that to 1 plus 3. Why don't you take 3 out and compare with 1 and 2?
Separately.
Yes. Because
yes, now you can do it now. If you look at all this, that is the example of a no orthogonal contrast. Is there now? That is deviation first, precision last. Okay. Remember, you take 3 and which is the last. Okay. You compare with each of them. Is another way.
Yes.
It depends on the way you want to. Okay. You know, it depends on the way you want it to be. It depends.
So does it mean your study? Yeah, in your plan contrast now, we have not, what I'm trying to say, it seems you've not exhausted all the possible contrast options.
And which other one do you think is possible? Because all the options possible is what we put. We only use the helmet orthogonal IMF for this one we are doing. But all those options there, okay, let me go there. These are the possible ways you can combine. Look at all this. Okay, for example now, for our own 3 group now, look at the possible ways. So is there any other way? Is there another way you can use to do this thing? Yeah. It's possible, but is there any other one? Different way you can arrange.
Look closely now. Let's look at deviation first.
It's like combination. What do you say?
So I'm just trying to look at like these 3 groups now. 2 versus 1 to 3, 3 versus 1, 2, 3. Why don't you have 1 versus 2?
Which one? Which one are you talking about?
The deviation first, the non-orthogonal. It's as if there's still one more option that is
okay,
left.
The deviation first. Okay.
Yes.
What did you? Okay. If you look at it,
I'm looking at.
So you want 1 to compare with all of them?
Exactly. Why are we not comparing one with all of
Well,
them?
I think the issue there is that because the rule that the contrast should be 2, it should be number of group minus 1.
Okay.
Because it will amount to you doing even the what we are talking about, the t-test, where we say we are family-wise
Yeah.
where you are now doing too many tests. You understand me now? This
Okay.
contract is just to break this into 2 stages, 3 group, 2 stages test. If it is 4 group, 3 stages test. You get it now.
So for
And
3
sir,
groups.
sir, the rule also says except first, which means except one.
Okay,
Yes.
except one.
Yes.
Yeah.
Yes.
I've seen it now. That explains it. Thank you, sir.
Yes.
Thank you.
Well done.
But that except first, will it not affect? Well, maybe when we start practicing and doing it, then you
Even to be sincere
start.
with you, if you look at it, orthogonal contract make more sense, because to me, when you compare two with all of them, you are trying to see, okay, you are comparing two with the average of them. Yes, I mean. So if you find out that the two is greater than the average or whatever, how will you interpret it? So if you look at it, although there are different scenarios that may warrant that, but I think the orthogonal is more straightforward. It's not more straightforward, and the orthogonal also depends on the way you see it and the way you code your this also. For example, now in our situation now, we quote the placebo as number 1. Then some people, the placebo may be number 3. They may say experimental 1, experimental 2, and placebo. Their control may be number 3. Their control may not be number 1. You get it now? I don't know if you understand me.
Yeah. Yes, I understand.
This thing is just a matter of you just knowing, all these things, experimental research in those days, there are many groups to deal with. They're the one that develop all this. But gradually it's fading away, because as you go to see, it's a matter of time. Anova will give way to regression. You give way to regression. Instead of doing Anova, people just go and do regression. Okay. Should we continue?
Yes.
Should we proceed?
Yeah.
Okay, let somebody run. Let somebody run. Who will run? Dr. Balogun, have you?
I'm true. I understand. Yes.
Yes. Do you have your data there? Can you run? Or Dr. Ebenezer should run it again. Who will run for us?
Okay, let me run.
Okay.
Okay, analyze.
Yes, that's good. You are there. Now analyze.
Compare me. Then I'll go to one way Anova.
Yes, sir.
It's already
go to contrast. Yeah, go to contrast.
So I'll just go straight to contrast.
Yes.
Then I'll click polygonal.
Polynomial, yes, it's okay.
I'll put polynomial.
Yes, okay. Leave it as linear. Leave it as linear. Leave it as linear. Yeah. Okay.
So now, here I'll put in a.
If you look at it, say contrast 1 of 1. Wait, 1 of 1. That is, you want to do contrast 1. Number 1 is the low dose. -2. No, according to the
-2.
-2.
Okay, -2.
No, the way you code it, so we enter. Wait, doctor. Wait.
Okay.
Wait, let me explain. No, with the way we enter low dose as 1. No, placebo as 1. Low dose as 2. High dose as 3. You get it now? Now, you now say contrast 1. If you remember our contrast 1, placebo was the one that we code as is the number 1 in our hierarchy, and the value of the contrast is -2. You remember? Placebo is -2. I don't know if people are following. For contrast 1.
Yes, sir. We are.
Yes,
if you know,
yes, -2.
1
yes.
of 1. Yes, -2. So that's why I say hard now. Hard. So you have to start with the way you code it. Placebo is number 1, so it's -2.
1. So the next one is 1.
Yes. 1 hard. Another one hard.
My ad is not showing again.
No, it's you because of the way
What
you
happened?
remove that.
Okay, let me remove.
No,
Let me start again.
It's the way you were doing your hand.
Again.
Yeah, one, hard.
Okay.
Yeah, go back there. One. Don't move around.
It's not a. Okay, it has entered now.
It's good that you're here.
Okay, so I'll go to next.
Yes.
I should go to next.
Next, yes. Now,
The next one is what?
Contrast 2 now. Is 0. Placebo is 0 for contrast 2. Yes.
So I'll not add that one now. So that add 0.
0, yes, put 0.
Okay. Then the next one.
The other one, the low dose is -1 for contrast 2.
-1.
Yes.
-1. Then the other one is 1.
Is 1, yes. Add
it's 1.
Add it.
So are we done?
Finish now. No, we are finished. Okay, wait.
So I
want us to continue. Click continue.
Okay.
Then I want you to click option. Click option. We'll have click option even when we were analyzing before. Click option. Doctor, click options. You are put yourself if you want him to hear you. Click options. Dr. Ebenezer. Descriptive is descriptive.
I am packing up my phone blocking. My phone was ringing.
Okay. Yes, descriptive. Click on descriptive. Descriptive.
In an online class. I'm in an online class. I'm very sorry. No
problem.
Because I'm using my phone for the system.
You go to.
So
you have to be using Wi-Fi because the phone will disturb. Okay,
my Wi-Fi is slow.
Okay, descriptive.
Where do I click now?
Descriptive. Click on descriptive. It's up.
I can't see it again on my system.
It's on top.
It's there now. Are you not seeing what we are seeing? It's you that you are showing us now.
But on my system, what do I click now? It's only showing the Zoom. The other side, I can't see it again.
No, it's you that went out. It's you that went out of the. Go inside the Zoom and,
How do I come back? How do I come back?
If you are in the Zoom, go and share. Share again and go and click on the something. Share. Click on share in the Zoom and enter it.
Unless
Okay, stop sharing and share again. Stop sharing and share again.
Sorry. Let me do it again. Sorry for the inconvenience. Let me just. So I am now on descriptive.
Yes. Click on descriptive.
See where I am now.
Click on descriptive.
Okay.
We were seeing it before. It's you that were not seeing. Well, continue.
Okay.
Continue.
That's okay.
Okay, yeah.
Okay.
So you have to share your output. If you don't know, stop sharing and now go and share the output. Stop sharing and share the output. Yeah, share the output for us.
This is the output now.
Yeah. Can you see? So if you look at it, there are this descriptive. This is the descriptive we did. 2.2. Can you see all the mean, standard deviation, those stuff? Then look at the Anova. If you look at it, the one you did before combined is the one you did without contrast. If you remember, the p-value is 0.025. Then now this is your contrast. When you had your contrast now, this is what your contrast are accounted for, and this is the deviation. Now you scroll down. I think there is. Thank you. Now, if you come to the contrast, can you see now? Look at the value of the first contrast, 3.8, and look at the T. So the first contrast is significant. You compare the combination of low dose and high dose and the placebo. It shows you that low dose and high dose, that is, there's a difference between people that take something and people that didn't take anything. Look at the P 0.29, 029. Then the second contrast is it compares high dose and low dose and high dose. Now, it's almost significant. Almost significant. So, what he's telling you is that there's no much difference between low dose and high dose. But when you compare the combination of low dose and high dose and placebo, if you look at the something, if you go and calculate the mean, it shows that the difference is significant. That's just interpretation. And you see this contrast, it gives you two options. Assume equal variances, does not assume equal variances. If you remember when we do t-test, when you run t-test, it's run 11 tests of equality of variance to see if the variances are the same, homogeneous or not. Then it will now give you, in case your variances are not equal, they are not homogeneous, it will give you two sets of answer to choose one from. Will you assume variances? No, when you was clicking, after clicking the script, you can click on homogeneity test to test for equality of variance. We'll have done that, but you can even go back and do it. So
I do it.
It's contrast for you. I don't know if you have questions concerning this. So at least it's able to tell us something about, okay, where the difference lies. So after this contrast, we are going to post up. That one is a different ball game and it's different. Though it's easier to conceptualize than blank contrast. Should we still do that or we do it tomorrow because it's 9?
Tomorrow, sir.
It is tomorrow. It's 9 o'clock. Tomorrow.
Okay, stop sharing.
Tomorrow.
Let's go and digest this one first.
Stop sharing. Stop sharing, sir.
I'm stopping. I've stopped.
Okay. I will upload something and share with you. I will upload let me see. Any question? Any question?